Understand the thermodynamic relationship between the equilibrium constant, Kp, and Gibbs free energy, delta G degrees. The equilibrium constant of a reaction is directly related to the standard Gibbs free energy change by the equation delta G degrees equals RT ln Kp. Alternatively, this can be written as Kp equals e to the power delta G degrees slash RT for a reaction to have a massive equilibrium constant. Kp equals 2 times 10 to the power 30. The value of delta G degrees must be highly negative, highly spontaneous. Connect delta G degrees to enthalpy, delta H degrees, and entropy, delta S degrees. The Gibbs free energy change is determined by both the enthalpy and entropy changes of the reaction. Delta G degrees equals delta H degrees, T delta S degrees. To make delta G degrees highly negative at a standard temperature of 298 Kelvin, we need a highly negative delta H degrees, highly exothermic, and or a highly positive delta S degrees, highly increased disorder. Calculate the overall reaction enthalpy, delta H degrees, using Hess's law. Since enthalpy is a state function, the overall enthalpy change of a multi-step reaction is the sum of the enthalpy changes of its elementary steps. Step 1, delta H degrees 1 is equal to plus 242 kilojoules per mole of reaction. Step 2, delta H degrees 2 is equal to plus 4 kilojoules per mole of reaction. Step 3, delta H degrees 3 is equal to minus 432 kilojoules per mole of reaction. Delta H degrees overall equals 242 kilojoules per mole plus 4 kilojoules per mole plus minus 432 kilojoules per mole equals math 186 kilojoules per mole of reaction. The overall enthalpy of the reaction is large and negative, strongly exothermic. Evaluate the contribution of entropy, delta S degrees, to the reaction. Look at the states of matter in the balanced overall equation. H2 plus Cl2 is in equilibrium with 2HCl. There are exactly 2 moles of gas on the reactant side and 2 moles of gas on the product side. Because there is no change in the number of moles of gas, the overall change in entropy, delta S degrees, will be very close to 0, small and positive/negative. It does not contribute significantly to the massive value of Kp. Synthesize the findings. Since delta S degrees is tiny, the thermodynamic driving force that drives delta G degrees to be highly negative, making Kp extremely large, is almost entirely due to the fact that delta H degrees is large and negative, minus 186 kilojoules per mole of reaction. This matches option D. The correct answer is option D. The value of delta H standard for the overall reaction is large and negative.